All right, let's go through your Newton's Laws webquest review. So you should have already completed your third law ed puzzle. If not, it is homework. You got to finish it up. It is a grade. It'll be due on Monday. Please study. You have your CFA on Monday. Okay, so all of these links are in the agenda. So this is kind of what it looks like. You can see it on your paper in front of you. So we need to write down Newton's first law. So your pencil should be up and you should be writing. So Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. So please write that down. This can be paused. So students are writing it down. Put your pencil down when you get done. So finish writing that and then move on. So here is this first link, Newton's first law video. So we're going to be describing the examples. Describe the examples of the apple orchard and how it relates to Newton's first law. So kind of jot it down as you're watching, then we'll go through it together.
Welcome to Newton's first law of motion, the law of inertia. Sir Isaac Newton was an English mathematician, astronomer, physicist, and philosopher. He lived during the last days of the Renaissance period, and his work in physics laid the foundation for the modern age. His book, Mathematical Principles of Natural Philosophy, first published in 1687, laid the foundation for classical mechanics. In the book, Newton outlined his understanding of motion. His understanding became the driving force for how all scientists understand the physical universe today. For the past 300 years, Newton's helped scientists understand how comets move through the night sky, how waves and tides collide with the shore, and how planets move through the universe. Even today, if you're trying to explain how forces affect any object, including an apple falling from a tree, it lying on the ground, or that same apple being thrown across the orchard, you're going to want to use Newton's laws. His first law of motion sets the stage for how everything in the universe is related. An object at rest stays at rest. An object in motion stays in motion at a constant speed in a straight line unless acted on by an external unbalanced force. Newton's first law is all about inertia. It describes why an object has the tendency to keep doing what it's doing. Throughout the universe, moving objects like to keep moving, and resting objects like to rest. Basically, if you want to change an object's inertia, you need to use force. An object at rest stays at rest. The fallen apple stays on the ground. Newton's first law explains that the apple will keep doing what it's doing. Every object resists a change in its state of motion. The apple stays where it is. That is until your little brother picks up the apple and throws it across the orchard. Then we're on to the second part of Newton's first law. An object at rest stays at rest unless an external unbalanced force acts on it. I'm not saying your little brother is unbalanced, but he's using an external unbalanced force to launch the apple across the orchard. He's using the strength in his arm to pick up and throw the apple, which is greater than the resting force currently acting upon the apple. In this case, the apple's ability to remain at rest has been overpowered by an external and unbalanced force. It's now flying across the orchard. Next, we get to an object in motion stays in motion at constant speed in a straight line unless an external unbalanced force acts on it. The apple now continues in a straight line across the orchard until it falls back to the earth after hitting a tree, hitting a fence, or encountering enough resistance in the air to stop its motion. Any of these act as another external unbalanced force that changes the apple's state of motion again, and causes it to return to a state of rest. Unless, of course, your little brother runs after the apple, picks it up, and starts the process all over again. In summary, Newton's first law states, an object at rest stays at rest. An object in motion stays in motion at a constant speed in a straight line, unless acted on by an external unbalanced force. That apple could be anywhere by the time you're ready to take him home. Thanks, Newton. Newton's first law of motion, the law of inertia.
All right. Let's get out of here. So you should have had potentially at least 3 things written down for this. I mean, so that apple was at rest. Okay, sitting on the ground, it was at rest. And then it said, until your brother's unbalanced force of picking it up had done that. And then the apple is going to keep going once it was thrown until it hits something or it encounters air resistance. So please jot those 3 things down. Pause it. So please pause this until everyone is done writing. Then you will go back once we're done going through this, and you will complete this one on your own, clicking on that link. Okay, so then we have the next section. So it says we're going to go to this following site. We're going to click on the friction tab, figure out the simulation so that you know how to use it. Click everything in the yellow box in the right corner. Click reset every time that you start over. And you're going, then the 50 kilogram box should be on the ground. And I have the paper in front of me so I can look at this again. Slide the applied force to 200 newtons or approximately 200 newtons and hold until the speed of the box gets to around 12 meters per second and then let it go. Okay, so let's click on this. So it says we need to click on the friction tab. So we're going to click on the friction tab. Then, okay, so click everything in the yellow box. So click everything in the yellow box. And the reset button is right here whenever we need to reset it. The 50 kilogram box, yep, there it is. 50 kilogram box should be there. Slide the applied force. Okay, so here's applied force. We're going to slide it over to about 200 newtons, and we need to have it hold its speed until it gets around 12. So here, 12 meters per second squared. So we're going to answer the question, what happens to the speed of the box when you no longer apply the force? Okay, so let's do 200. Okay, so about 200. Oops, I went too far. All right, so what's happening? I went a little bit too much. Okay, got over 12 meters per second. Let it go. Okay, so what happened to the speed of the box when you no longer applied force? Okay, so what happened when you no longer applied force? Well, it slowed down, didn't it? Okay, it slowed down and it came to a rest. Okay, so then let me do this again. It says name all the forces that are at work on the box once we let it go. So let's do this again so you can see. We're going to hit reset so we can see this. Okay, so let's get it to 200 and then I'll stop. Close enough. Okay, it's getting to 12. Oops, too far again. Okay, so look, now it's the friction, and name all the forces. So we had friction was involved. Okay, so then what else? Let's see what else was involved too. Let's do this again. So sum of forces values. Okay, let's do this again. Let's look at all the forces that are on it. Look at, there's friction force, right? Oops. Friction force. There's applied force. What's pulling down on it? Gravity's pulling down on it. And then what's pushing up? Normal should be pushing up on it. So we actually kind of had 4 things. Okay, I know that normal and gravity were not included in that, but those are also involved. Applied friction, gravity. I should have had normal on there, so go ahead and you're going to add normal. So write down applied and friction, because those were your opposite, your pairs, and then gravity and normal. Okay, so write it down, pause it if we need. As the box is speeding up and moving to the right, are the forces acting on the box balanced or unbalanced? Okay, so remember, balanced is when there's no acceleration. Okay, or it's not moving. So if I'm doing this, look at, are they balanced? It says friction force is 94, but the applied force is 229. Okay, so they are not balanced. Okay, and we know that because it's speeding up. Okay, or it's unbalanced because the box is speeding up. And then that last question that you can't really see down here, why does the box stop? That should be very apparent. You should know that it's not, or it stops because friction is slowing it down. Okay, there's a force acting on it that's making it slow down. So look at, see, friction force is slowing it down. That's why the box comes to a stop. Okay, so let's go. Let's see what's next. Okay, so then you have these. Okay, you'll do on your own. So you'll go back to it. Make sure you click everything in the yellow box. Okay, and it tells you what you need to do. Okay, reduce the friction. Slide the applied force to about 200. Wait till it gets about 12. So then you have to kind of do some of those, what I did, redoing it over and over again to make sure you get all that. All right, next page. All right, next page we have Newton's second law. So Newton's second law is, we're just going to shorten it to force equals mass times acceleration. So go ahead and write that down. Pause as we need to. Then we have a video to watch describing the examples of the apple and the pumpkin and how it relates to Newton's second law. Okay, just so you remember, acceleration and force have a direct relationship. So if one goes up, the other goes up. If one goes down, the other goes down. Mass and acceleration are indirectly. So if mass goes up, acceleration goes down. But if mass goes down, acceleration goes up. So kind of keep that in your brain as we watch this video. There's going to be two things that you should have written down for this.
Welcome to Newton's second law of motion, law of acceleration. Sir Isaac Newton was an English mathematician, astronomer, physicist, and philosopher. As we learned in the first law video, Newton's revolutionary work during the late 1600s set the stage for how today's scientists understand the physical universe. His first law predicts how objects behave when forces are balanced. His second law tells us how objects behave when the forces aren't balanced. The acceleration of an object is directly proportional to the net force and inversely proportional to its mass. The second law is dependent on two variables, the net force in action and the object's mass. As the force increases, so does the object's acceleration, and vice versa. Also, as the object's mass increases, the acceleration decreases, and vice versa. Back to our apple orchard. Newton's second law gives us the relationship between the size of the force and the resulting acceleration. If your little brother throws one apple in the orchard, it goes this far. If your little brother hauls in a catapult and uses it to throw the same apple, it leaves the orchard, crosses the road, and ends up in the neighbor's field. The catapult uses a much larger net force to apply more acceleration to the apple and send it flying farther. Much, much farther. The other part of Newton's second law, as the object's mass increases, its acceleration decreases, can be demonstrated in the same way. Using the same catapult, your brother can send a giant pumpkin flying a much shorter distance than a tiny apple. The pumpkin has a greater mass, so the acceleration is smaller. The catapult could send an apple tree even less far. The larger the mass, the smaller the acceleration force. Unlike your brother's rather unscientific demonstration, Newton's law can be written as a mathematical formula. Combining the effects of net force, mass, and acceleration turns into acceleration equals net force divided by mass, or net force equals mass times acceleration. You can use either of these formulas to find the missing variable in algebraic problem solving. In summary, Newton's second law states the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. Now, find out how your little brother got hold of a catapult. Newton's second law, the law of acceleration.
Okay. So that one too. Okay, so describing the examples and how it relates to Newton's second law. Okay, he did talk about, the force and the mass. So we should have these two things. So a larger mass is going to equal less acceleration. Oh, sorry. I guess I only had the one on there. I thought I had more. Okay, because if the brother uses that catapult, which uses more force to throw the apple's going to go farther. Okay, but if the brother puts a pumpkin on the catapult, the pumpkin has more mass and it's going to travel a shorter distance. Okay, so that's kind of what that was relating to, describing those examples. So I didn't mean to show you this part, but start writing this down right here, and then you're going to finish it on your own. You're going to write, so go ahead and write this down when it says, when more mass is added to the body, and then you need to finish that on your own. When more mass is added to the body, and then finish it on your own. So you're going to go here, you're going to click on the upper right corner, okay, and tells you what to do to set all this different stuff. So double check that, go through it. Okay, so you do that on your own. Okay. So, and by the way, don't forget then you have this other video right here. Okay. Next section, this is kind of cool. Click on net force. Make sure everything's checked in the yellow box. Okay. So you need to predict. So I'm going to wait here a second. So predict which direction the wagon's going to move. Okay, so we have the same size person. Okay, same size person on either side. This is supposed to be the same placement on the rope. So my bad. They're supposed to be in the same place. Okay, they'll be in the same place. I know on your paper it shows them that they're in the same place. Okay, so ignore the fact that this one shows that they're not. Same place. So same size, same place. Okay, so the left force is 50 newtons. The right force is 50 newtons. Okay, so is the wagon not going to move at all? Is it going to move left? Is it going to move right? Make your prediction. Let's go ahead and do this one. So we have same size, different rope placement. Same size, different rope placement. So this one right here, this picture is supposed to be down there. My apologies. Okay, so again, make a prediction. So the same size, different placement, and they still have the same amount of force in each direction. Okay, is the wagon going to not move? Is it going to move left or is it going to move right? So let's now check this out. So we are clicking on, okay, I gotta have this in front of me. Net force. Okay, we got our net force. Okay, make sure everything is checked in the yellow box. Yellow box. Okay. Complete the chart. Okay, so they're in, so we need to put them, so same size, and they're like on the second knot. Same size, second knot. 50 and 50. Okay, go. Okay. They're not moving. So I'm going to pause. So you should have written, I'm going to come back over to here. Okay, so some of the forces, it's 0 newtons. Okay, so let's 0. Circle it. You don't have to highlight it. Circle it. There is no movement, right? Okay, so then let's do back over here. We're going to hit reset. Okay. So then it says to do same size. Put them here. Same size, but different placement. He's way over here. Okay. Oh, some of the forces, values, speed. Okay, so it actually, so on your paper, here's where it talks about the Newton. So if I was to change this guy, look at it, shows you that it's 100. Okay, so make sure you're paying attention to that. That's what it's going to be. Okay. All right. So put that other guy back up there. So sum of forces is 0. So they're not going to move. It's the same, 50 and 50. Okay. So we should have, so you should have written this down. There's no forces moving, which means there's no actual movement. Okay, so you can do these on your own. So it's going to show you that you're going to have a bigger one. Okay, and you can see on your paper it's showing you that the bigger person, so different size, same placement on the rope. And then this one, different size, different placement on the rope. And again, writing down your forces, the number of the sum of the forces, and then the actual movement. So you'll go back and do that. So then what's causing them to, to move or stay still? What causes them? Well, forces. Forces is going to, unbalanced forces are going to make them move or stay still. So if they're, the same, they're never going to stay still. If they're unbalanced, you start moving. So pause that, write it down. You're going to answer that last question on your own. Now we're to Newton's third law. Okay, so Newton's third law is for every action, there is, for every action force, there is an opposite and equal reaction force. Okay, so let's watch this video. And we're going to again describe those examples.
Welcome to Newton's third law of motion, law of interacting force. Sir Isaac Newton, the English mathematician, astronomer, physicist, philosopher, and all-around scientific genius, changed our understanding of the universe. His laws of gravity, motion, and mathematics shaped how today's scientists view the world. His first law predicts how objects behave when forces are balanced. His second law tells us how objects behave when the forces aren't balanced. His third law explains how forces act and react with each other. Specifically, it states, for every action, there is an equal and opposite reaction. And to our apple orchard we go once again. This time, Newton tells us that every interaction has a pair of balanced but opposite forces. It helps us explain how the apple sits on the ground. The apple exerts a force on the ground that's matched by the force exerted on the apple by the ground. The apple's force presses down and the ground presses up with an equal force. Forces are always balanced and they're always opposite of each other. This means that if the first object pushes on a second object, then the second object pushes back on the first object with the same amount of force, but in the opposite direction. Say your brother gets bored of simply throwing apples or launching them from a catapult. He decides to move on to the big stuff and decides to tie an apple to a rocket. As the rocket sits on the ground, the upward force of the earth balances the downward force of the rocket. But once your brother lights the engine, it pushes the gas down and out of the rocket, and the gas counters by pushing up and away from the rocket. This sends the rocket flying into outer space. Once the engine loses its energy, the thrust from the exhaust isn't as great, which allows gravity to take over. The rocket loses height and comes crashing back to Earth. The apple slams the Earth and stops. Now the rocket and the ground are again balanced. Unfortunately, the apple has disintegrated. But that's another story. In summary, Newton's third law states, for every action, there is an equal and opposite reaction. And it's officially time for your brother to leave the orchard. Bye! Newton's third law of motion, law of interacting force.
Okay, so describe the examples of the apple orchard. So the apple is pressing down and the ground pushes up. Okay, equal and opposite. The rocket with the apple goes up because the downward force of the rocket's engines. Okay, again, that's our kind of our classic one that we've talked about. So pause it, write it down. Then you have the link for the strollers. Again, read through this. Read them, these little things in the italics, so that way you for sure know what's going on. You're going to describe the result of the F1, so force 1 and force 2 after impact. You have a video. All right. So you can see I randomly have these two things. So you have to predict what's going to happen. Okay. So we're going to have a red box that's going to be 5 kilograms, a blue box that's going to be 5 kilograms. One of them is going to move at 10 meters per second. The other one's going to be moving at 0. They're going to collide. What do you think is going to happen? Okay. So we're going to, I'm going to we'll do this. Uncheck momentum. So let's go ahead and let's do this. I'm going to do this. Okay. So it says we're going to uncheck momentum. Okay. We're going to enter 1 under the elasticity number. So here's this. So right here, we're going to enter 1. So you got to make sure you have that for all of yours as well. Okay, so then here's the run, the pause, the reset. Okay, then come down here. Uh-oh, I can't see. There we go. Okay. And we're going to have the red box, mass down here. Mass red box. It's going to be 10. The mass of the blue box is 5. Okay. And then velocity, or the speed, that's going to be 10. This is going to be 0. Okay, so 0. So you should have predicted. Okay, so that needs to get checked. You need to have, if you don't have the prediction written down for what you think is going to happen, then you're losing points. So predict what you think is going to happen. Okay, so let's run. Okay, so describing what happened. The red box did what, and the blue box did what. Okay, so you should have done your prediction. So you should have said, well, what happened? Well, the red box stops when they ran into each other, and then the blue box keeps moving in which direction? To the right. Okay, so you'll do this one on your own. You can see it's 10, and then there's negative 10. Still 5 kilograms. Now we're going to do this one. We're going to change it up. So I've reset it. Okay. So the mass of the red box is staying 5. The mass of the blue box is going to be 1. This is still moving 0. This one's moving 10. Okay, so we've made a difference in the mass. So write your prediction. What do you think is going to happen? Pause it to make sure you get that written down. Okay, run. Boom. Woo! Okay, write down what happened. So to me, it looked like that red box, so they collided. The red box slowed down, and the blue box accelerated. They both kept moving right, though. Okay, so what did I say? So both move to the right. The blue speeds up, and the red slows down. Yep, that's what I said. Okay, so again, you got to make sure you're telling me which direction they're moving, speeding up, slowing down, stopping, that kind of thing. Then you have that one more last question at the very bottom. Okay, so you need to finish this up on your own. The links are on the agenda. Second law lab and conclusion needs to get finished. It's going to get collected on Monday. Okay. Study guide, because I'm not here, it's going to be collected on Monday. Study guides due Monday because you have your test on Monday. Keep it. You're not turning it in. Actually, the second law lab and conclusion, you can turn any of that stuff up into the front tub, but the study guide you need to hold on to. Anchor book, work on it. So again, links are in the agenda for the webquest. Finish it. You can turn it in to the tub up front. When you're done, work on the second law lab and conclusion. If it's done, you can turn it into the front tub. Otherwise, you need to finish it. Study guide, complete it. Test is on Monday. You're holding on to it. Okay, get working.